So picking up where we were, we had just finished talking about mole-to-mole conversions, but we don't usually measure things in moles, we measure in masses. And so the big idea here is mass of the starting compound, and you're going to convert to moles of the starting compound, and then to moles of the other. There's always this moles of one thing to moles of another thing in the middle. And that's the relationship that comes from the balanced chemical equation. That gives us relationships in numbers of particles or in moles of particles. It does not give us mass ratios. And then we convert the moles of product or thing we're interested in into mass. So another way of expressing this is grams to moles to grams. And that is the theme of stoichiometry. So you know that you're doing it, you're studying enough if you wake up in the middle of the night mumbling grams to moles to grams.
How'd you know?
Yeah, so that's the key. It's grams to moles to grams. So stoichiometry is a technique, and there's lots of different questions we can ask. So there's not really anything that you can just memorize. You have to learn how to solve the problems. But the common thing in most of these problems is grams to moles to grams. And then there are some variations on that we'll learn as we go along. Okay? So let's do this example, getting back to our CO2 example. According to the U.S. Department of Energy, the world burned 3.1 times 10 to the 10th barrels of petroleum in 2010, which is the equivalent of approximately 3.5 times 10 to the 15th grams of gasoline. Calculate the mass of carbon dioxide emitted into the atmosphere using the combustion of octane as the representative equation. So this is an approximate calculation, right? This value of 3.1 times 10 to the 10th barrels, that's an estimate. That only has 2 sig figs. It's useful information, but we're not going to be calculating to the nearest tenth of a gram how much CO2 was given off. We're also saying, well, that would be the equivalent of this much gasoline, so there's some estimation in there. And then the gasoline is not all octane. We're just saying, well, this is a good representation of the type of reaction that occurs. So lots of words in there. We need to take the words and write take the numbers, forget the words. Take the numbers and write them under our balanced chemical equation here. My pointer's acting up. So that we can figure out where we're starting and where we're going. So this 3.5 times 10 to the 15th grams of gasoline. We're going to pretend that that's octane. So I'm going to write that down here, 3.5 times 10 to the 15th grams. We've got a fruit fly. And then what are we trying to find? Mass of CO2. So question mark under CO2, and we're looking for the mass. Grams is a nice unit. Okay? And then after we figure that out, we're going to compare that result to volcanoes, which produced about 2 times 10 to the 11th kilograms of carbon dioxide per year. But I'm going to erase that right now because that's not part of this calculation. So what's the path going to be here? Grams to moles to grams. We're going to start with grams of octane, convert to moles of octane. Then we're going to convert to moles of CO2, and then to grams of CO2. So we're combining several individual things that we've done before. We've converted grams to moles, and we've converted moles to grams. That uses the molar mass. The new thing that we learned is how to do moles of this to moles of that. But that's even easier than the molar mass thing. So now we just need to put them together. So I'm trying to write with white. That doesn't work very well. 3.5 times 10 to the 15th grams It's important in stoichiometry to write grams of what? Times, and we're going to go to, this is going to be way too large. We're going to go to moles of C8, H18, and then we're going to go to moles of CO2, and finally we're going to get to grams of CO2.
Does the 2 in front of the gas right there, does that matter for anything?
Does this 2 matter?
Yeah.
It does. But that's going to come into the mole to mole ratio. So we're not going to look at it yet. Right now I'm just doing grams to moles to grams and getting all the units to work out, and then we'll pull numbers in and we'll find that we are going to use that too. Moles of CO2. And moles of C8, H18. I really should take a survey of my videos and catalog all the interesting background noises. Yesterday, there was a fight in the other lab, and I had to pause.
Like a fist fight? Why?
2 girls fighting. There was hair pulling involved. Just, and there was a baby crying, and the muffler, and the fire trucks, and the police cars, and just on top of the trains. Okay. What train? We don't even hear the trains anymore. Okay, so I got the units in place. Any questions about the units? You okay with the units? Now we put numbers in. I think this one in the middle is the easiest. Moles of CO2, moles of octane. The numbers for this come from the coefficients of the balanced chemical equation. So this means 2 moles of C8H18 is going to form 16 moles of CO2. Does that make sense? So that's where the 2 comes from, and then why the 2 is important. So we get 16 moles of CO2 for every 2 moles of octane that is burned. Okay? How do we convert from grams to moles for octane? We need the molar mass. So one of the things you can do with significant figures is to just think about them a little bit before you start doing all kinds of crazy calculations. This number here only has 2 significant figures. So my answer can't have more than 2 significant figures. So whether I use my memorized 4 sig fig molar masses, or I use the ones off the periodic table on the wall that have 5 or 6, it's not going to affect the outcome, right? I still don't want you to round things to whole numbers. So I'm just going to use the ones in my head because it's easier. So C8, H18. We've got 8 carbons times the mass of carbon. And we've got 18 hydrogens times the mass of hydrogen. 8 times 12.01 plus 18 times 1.008. 114.224. Molar mass has units of grams per mole. I'm having an argument with my husband's iPad here. So 114.224. Now technically that would only have like 4 secrets, but it's going to be limited by this, so I'm just choosing to overlook it.
And it overall makes your answer more correct if you do more. Say, like,
If you have,
in the
you want to have at least, I would say at least 2 digits more to avoid rounding errors, right? So I wouldn't want to round this off to 110. That would be 2 sig figs, and so it wouldn't be less than this, but that's going to cause some error. And then CO2, I'll write that one out even though I know what the answer is. CO2 is 12.01 plus 2 times 16, which is 44.01. There's some days that you just really want to be able to just reboot the whole day. This would be a good day for that. I don't see it getting better anytime soon either. Okay, so I've got 3.5 EE15 divided by 114.224 times 16 divided by 2. Yes, you could simplify that. I really don't see the point. Times 44.01 equals. And I'm getting a really big number. 1.078, which would round to 1.1 times 10 to the 16 grams. Yes?
So, kind of related to this, but kind of for everything, when do we know and to use the 6.02? When do we know to use Avogadro's number versus when not to? Because I think when I'm doing these kind of things, I see the scientific notation and think that I have to use that.
Okay, so the question is, how do we know if we need to use Avogadro's number? Because when we see big numbers like this, we think, oh, well, I'm going to need to use Avogadro's number. So we taught you Avogadro's number, and it is important. We're not going to use it very much at all in the rest of the semester. That's the honest truth. It has to do with numbers of atoms. And there are certain calculations where we need to know numbers of atoms. But most of the time, we're just counting atoms by weighing them, and so we use moles instead because they're much nicer numbers, aren't they? We're dealing with, oh, half a mole of this or 5 moles of that instead of these huge numbers of atoms.
Okay.
So most of the time, we're not going to use Avogadro's number. Any other questions? Well, let's see how that compares to what the volcanoes put out. So this was the answer we got from combustion of petroleum products. Volcanoes, this converted from kilograms to grams, 2 times 10 to the 14th grams. So that is a difference, right? It's a little hard to look at and figure out, well, is that a huge difference? Is that a little bit of a difference? So we could see how many times larger the one is than the other. The petroleum combustion, this is 55 times that of the volcanoes.
And how did you find that?
I took this number, 1.1 times 10 to the 16th, and divided by 2 times 10 to the 14th. And that gives you about 55. So 55 times more CO2 from human activity than from volcanoes, which suggests that we're at least contributing to any increases in CO2. Any questions? Let's do another stoichiometry problem. Magnesium hydroxide, the active ingredient in milk of magnesia, neutralizes stomach acid, which is primarily HCl, according to this reaction. And the question is asking us what mass of HCl in grams is neutralized by a dose of milk of magnesia containing 3.26. I know he's going away now, and he won't come back probably because I shut the door. But Dose of milk of magnesia containing 3.26 grams of magnesium hydroxide. All this stuff at the top is story. We don't need that to solve this. We need the balanced chemical equation. We need our question here, what mass of HCl in grams? So I'm going to write under HCl, I'm going to write question mark, grams. And then we need this. So this person is going to take 3.26 grams of magnesium hydroxide. And we want to know how much stomach acid can that neutralize. What's our path? Grams to moles to moles to grams. So we start out with grams of magnesium hydroxide. And I'm going to convert to moles of magnesium hydroxide. And then I'm going to convert to moles of HCl. And then to grams of HCl. That's the path, grams to moles to moles to grams. Notice, we're changing one thing at a time. In this first step, we're changing from grams to moles of the same compound. In the second step, the unit stays the same, moles and moles, but the substance changes. And in the last step, we change moles to grams, but the substance stays the same. You can only change one thing at a time. Then I'm going to put the units in so they cancel out. And this will be grams of magnesium hydroxide. The middle one, the mole to mole ratio, is the easiest. What number goes in front of HCl? 2. Because there's a 2 in the equation. What goes in front of magnesium hydroxide? 1. A 1. So that's good. And then we need some molar masses. So for magnesium hydroxide, 24.31? Yeah. So 1 magnesium, 24.31. How many oxygens? 2. 2 oxygens. How many hydrogens? 2. 2 hydrogens. (24.31) plus 2 times 16 plus 2 times 1.008. 58.326. Grams per mole. And I'm glad I shut the door because here comes another train. And we're going to need HCl as well. 1.008, 1 hydrogen and 1 chlorine. And that's going to give us 36.458.
Why didn't we do, oh yeah.
So I'm going to put the molar mass for HCl where the unit grams is. And I'm going to put the molar mass for the magnesium hydroxide where the unit gram is. And then we multiply and divide. 3.26 divided by 58.326 times 2 times 36.458. How many sig figs should the answer have? 3. So this is 4.08 grams of HCl. Any questions? Yes?
How come this is so much easier than what my chemistry teacher in high school tried to explain?
Why is this so much easier than when his high school chemistry teacher tried to explain it?
Because it's familiar to you now.
Because I'm just so awesome.
And that's my
No, probably because you've heard it before. And sometimes it takes 2 or 3 times. When I took high school chemistry, it was honors chemistry. My first time, I got an A. I had no idea how.
That's how
I'm almost like, okay, I'll write stuff down. Had no clue what I was doing. Went and took the equivalent of this class my first semester in college, and it was like, oh, that's what he was talking about. And all of a sudden everything became clear because I'd heard it before. Chemistry's kind of a circle, and you have to go through all these different topics, and then when you go through it again, it starts to make sense. So that's just kind of how it is. Any other questions? Stoichiometry is an essential part of chemistry. These calculations are really, really important. There's some other things I've told you, it's like, yeah, you could get along without that. If you don't get stoichiometry down, you're probably not going to pass the class. So this is really important. Do you want to do another example? I heard one no. I'm kind of going with that, but that's okay. A component of acid rain is nitric acid, which forms when NO2, which is also a pollutant, reacts with oxygen and water according to this simplified equation. That's all story. The generation of the electricity used by a medium-sized home produces about 16 kilograms of NO2 per year. Assuming there's adequate oxygen and water, what mass of nitric acid in kilograms can form from this amount of NO2 pollutant? Well, there's a whole bunch of words in there. Focus on the numbers. 16 kilograms of NO2. That's the only number in the problem. So let's write 16 kilograms over here. What is the question asking us for? Kilograms of HNO3. What mass of HNO3 in kilograms? So over here, question mark, kilogram. What is our stoichiometry path? Grams to moles to moles to grams. But we're starting with kilograms.
If we're going from kilograms to kilograms, can we just...
If we're going from kilograms to kilograms, those conversions are going to cancel out. So I'm going to show you how to do that, okay? So let's just start here. 16 kilograms of NO2. Oh, iPad. Now, what I want to do is I'm going to circle this kilo, and I'm just going to mentally take him out. I'm not going to look at him right now. We'll come back to him later. I'm just going to pretend he's not there, but we know that he is. So, grams to moles to moles to grams. So, to moles of NO2 to moles of HNO3 to grams of HNO3, and then moles down here.
But they want it in kilograms, so can we put the kg and circle the kg?
We'll get to it. We'll get to it. Yeah, we're just ignoring the kilo for right now. I know it's hard. And grams of NO2. So let's look at our units. Moles of HNO3, cancel moles of HNO3, moles of NO2, cancel moles of NO2. We can't cancel kilograms with grams, but kilo is a multiplier. It can be thought of like a variable. So I'm leaving the K there because we just kind of suspended him. And I'm going to cancel just the grams with the grams. The kilo is still sitting there. Is that okay? So when I look at these units, I've got grams here, and I've got this kilo that I didn't cancel out. So what does that give me at the end? Kilograms. So I canceled out grams of NO2 with grams of NO2, but I didn't cancel the kilo. I canceled all these other units, and then I've got grams here. So what's left at the end, unit-wise, is this kilo and that gram, and that makes kilograms.
Even though we're using all grams at the bottom?
Even though it's all grams at the bottom, because the gram here canceled this gram. Now, if that bothers you, feel free to put in a conversion here of, let's see, I had to get it right, 1 times 10 to the third grams per kilogram. And then over here, you're going to have 1 kilogram over 1 times 10 to the third grams. You can do that, absolutely. What happens to these, though? They cancel each other out. Okay?
Can you always do this? Like with other problems?
If you're starting, say, with milligrams or centigrams, and you're going to the same unit at the end that you started with, then yes, you can. If you're feeling just a little, I don't know, that sounds dangerous, then go ahead and do the conversions, okay? It's a shortcut, yeah. It's a shortcut, and so you don't have to take that shortcut. That's going to be way too slow. But I just want to show you that that's there. So you can put the conversions in. Another thing that some people will do is they'll just take this and convert it to grams separately, and then do this and take their gram answer and then separately convert it to kilograms. That works also. Okay, so we need some units some numbers in here. We got plenty of units. How many moles of HNO3? 4. How many moles of NO2? 4. And then we need grams of NO2. So that's 1 nitrogen plus 2 oxygens. Whoops. I'm multiplying in my head there. Oh, seriously. 14.01. What is that, 46.01? So that's for the NO2, 46.01. And then I need HNO3, so that's 1.008 plus 14.01 plus 3 times 16. $63.018.
And then for the mole part in the equation where you just have like mole NO2 and mole HNO3, can we put a 1 there just for a numerical value there?
So the question basically is, can you cancel these 4s?
No.
No?
Where it
Oh.
says mole of NO2 over the 46.
Oh, here?
Yeah. Can
Yes.
we have a 1 there? Just
You can have a 1 there. Some people just feel better if there's a number there. It's going to be 1. Somehow it doesn't bother people as much when it's in the denominator, but you can put a 1 there as well. That's a good question. And with the 4s, you can cancel the 4s out if you really want to. Or you can multiply and divide by 4. It's up to you. So we've got 16 divided by 46.01 times 4 divided by 4 times 63.018. And I ran out of space. I'll write it up here. How many significant figures should my answer have? Just 2. So I'm getting 21.9 So that's going to round to 22. And what is the unit? Kilograms of nitric acid. Any questions? Yes.
So, in my stats class, my teacher says that if you have to do a calculation, you have to have a 0.0 at the end if it's a whole number. Do we have to do that for your class or no?
No. Maybe statisticians do that, chemists do not do that.
Okay, cool.
Because to a scientist, 22 means there's uncertainty in the ones place. So, yeah, you have to know the conventions in the discipline that you're working in and just go along sometimes. Any other questions? Yes?
Did you just multiplied right across, you're gonna have to like times by 10^3?
No, because the kilo just stayed there.
It just
It didn't cancel out. Now, I did this problem a little bit differently with the Monday, Wednesday class. So if you want to see a slightly different explanation, you could go watch that one.
What was the difference?
The difference was in how I treated the kilo.